You're tuned into the Digital Ship webinar, Leveraging Machine Learning for Engine Predictive Maintenance. Joining us is Naveen Bhushan Hegde, Director for Propulsion Control and Optimization Product Line of Emerson, and Lars Stoustrup, CTO of Frugal Technologies. Type in any questions you have in the Q&A section, and we'll get them answered for you after the presentation. And now we'll hand you over to Carl Jeffrey, Founding Editor of Digital Ship.
Our topic today is using machine learning to do predictive maintenance on ship engines. So you probably know the basics of predictive maintenance already. Rather than do maintenance according to a schedule, like with a car service every year, we're going to do maintenance only when it's needed. So when we can predict that something will go wrong if we don't do the maintenance. So in machinery, there's often signals of something about to go wrong before it actually does go wrong. And digital tools with machine learning can detect these signals. We'd also rather not do unnecessary maintenance, so doing something earlier than we needed to, because maintenance is expensive and can cause new problems, such as if things don't get put back together properly. But there's also other benefits to keeping something continuously well maintained, not just stopping things from breaking, but it also means it runs more efficiently, so the ship engine's using less fuel. Now, predictive maintenance isn't easy. You need expertise in the data and the software side of it. You need expertise in gathering data from machines, filtering out bad data, and you need expertise in machine learning and statistical analysis, and you need operational expertise working out how to implement it in ways that don't overburden the crew. But we've got two speakers today with enormous expertise in all of this. We're going to hear from Lars Stoustrup. He's CTO of Frugal Technologies. They're based in Aalborg in northern Denmark, and they focus on improving propulsion efficiency with machine learning. He's got a background in lots of digital technology domains and statistical analysis. And we're going to hear from Naveen Bhushan Hegde. He's Director for the Propulsion Control and Optimization product line with Emerson. He's a former senior operational engineer on board merchant vessels, and he's joining us today from Doha, although he's normally in Singapore. Emerson is one of the world's largest automation companies, and it's made a strategic investment in Frugal Technologies. So we're going to talk today about ways you can clean data and then use the algorithms to get insight from it. And we'll also present Frugal's smart propulsion platform for engine predictive maintenance. So as usual in our webinars, we're going to have talks of about 30 minutes, then take your questions, and you can put your questions in the Q&A box at any time. And I'd like to invite Naveen to start the talk.
Thank you so much, Carl. Delighted to be on board. So Lars, if you can share the screen. And if you, yeah, thank you so much. Thank you, Lars. Okay, so firstly, good morning, good afternoon, and good evening to all who are joining from different part of the world. I'm Naveen Hegde, and I'm responsible for the propulsion control and optimization product group globally for Emerson. I'll be sharing my thoughts around leveraging machine learning for predictive maintenance. So if you can go to the slide number 1, Lars. So let me begin by laying the ground for our discussion. We know keeping the vessel operational is one of the top priority for a ship owner or a ship operator. If the vessel is not moving due to an engine failure, it can cause a massive impact to onboard and onshore team. Why I say so? I was also sailing, and I have been in similar situation where the engine got stopped in the middle of the ocean, and it was not a pleasant situation at all. The crew on board and the superintendent were all hands on deck till the time the issue was resolved. Sometimes it could take more than a day to make the engine run again. So if you ask me, a cylinder liner crack or a piston crown hole can happen more frequently than you expect. Again, the traditional maintenance on a scheduled basis or based on an accumulated experience involves inspecting and servicing vessel equipment at regular intervals. This can be few hundred or even 1,000 hours depending on the type of the maintenance. But this again lacks the insight which can be gained from machine learning or artificial intelligence. So why gaining the advanced insight into the predictive maintenance is so critical? What it can lead to if it's not there? So number one is on the untimely equipment failure, which can lead to the vessel downtime. It can be something which I mentioned before, a liner crack or a piston crown hole or something similar. There can also be a compromise on the safety of the crew when an equipment breaks down. And nobody really likes fuel leaking at 140 or 150 degrees Celsius. There can also be an expensive repair cost. You don't have an option but to stop the vessel and do the maintenance. Uh, the the engine is again unpredictable. You cannot rely on the engine. You have to go by the periodic maintenance, and of course the high fuel consumption cost due to the inefficient engine. So when the engine is about to fail, it is not running to the best of its efficiency. Its engine is about to fail, so it will always be, the fuel consumption will be high, the SFOC won't be that great. And last but not the least, there is also an impact on the emission compliance due to the delayed maintenance. Again, it's the same theory that the engine are not running at the best efficiency. You are consuming more fuel for the same voyage. So before we move to the next slide, let me just ask you a question. Imagine a scenario where instead of relying solely on a fixed schedule of maintenance, we use the wealth of data generated by the vessel to predict when the maintenance is needed. So this is where, if last we can move to the next slide. Yeah. So this is where Emerson, who supplies a lot of devices, intelligent devices on board, and we kind of collaborated with Frugal Technologies over here. So as a stakeholder for almost 50 years, Emerson has been in the marine space, and we are committed to serving the industry to meet its goal, be it the decarbonization goal, sustainability, or even the efficiency goal for any ship owner or a ship operator. So we do have the micromotion Coriolis meter, the Aventix propulsion control system, and we are also able to provide a lot of data which can be leveraged to make meaningful decisions. So what we did was that we did a strategic investment in Frugal Technologies, where we launched the smart propulsion. And this solution not only helps to reduce the fuel consumption by up to 15%, but there is also a benefit which is on the predictive maintenance, and which we will be talking today. But let us understand the benefits of this predictive maintenance before I pass it to Lars to go into more technical portion. Yeah, so Lars, if you can help me. Thank you. So if you see the product, the predictive maintenance under smart propulsion, this basically is helping you in 4 key things. Number 1 is on the enhanced vessel performance. So here the solution basically identifies the exact location and the nature of the potential issue on board to ensure each component operates at a peak efficiency. So imagine looking at understanding that the cylinder liner crack might happen in the next few days or few months, and taking precaution to avoid it. This particular system gives you the data for each of the equipment on board. It shows you the trend, whether it is deviating from an expected process parameters. The second one is on the cost reduction, and over here the solution helps to foresee when an equipment failure or degrading equipment efficiency is likely, allowing for any intervention before there is a costly repair and maintenance, or even when the vessel is not running to the best of its efficiency. The next one is on the reduced idle time and the environmental impact. Here again, as I mentioned before, this helps to reduce the downtime. The CO2 emission aligns with the environmental standard and also reduces the vessel carbon footprint. So you are always running the engine to the most operationally efficient as it is possible. Last but not the least, on the operational and the financial advantage, so the system continuously anticipates and prevents any failure and improves any operational reliability. So you are running the engine at the best SFOC. If there is any failure or any deterioration on any of the parameters, this can be seen well ahead and precaution can be taken for that. So to conclude, I can only say that precaution is much, much cheaper than cure. And this solution definitely helps in that regard. So with that, I would like to pass it to Lars to go through the technical portion of the predictive maintenance. Thank you for listening. Over to you, Lars.
Thank you very much, Naveen. Yeah, so first I'd just like to say thank you to those of you who managed to join us at SMM last week. It was quite the event, and what we're talking about today, we also actually brought to SMM. We had a very nice demo set up. At least we think it was very nice. That had a part of it was showing off exactly what we can do with predictive maintenance, and it's basically some of the same stuff that we want to talk about today. Now, everything we do in predictive maintenance, and also in the basic fuel saving product that we have, which is the frugal propulsion setup, is based on modeling. And when you want to do something modeling wise that takes its outset in data, you want to make sure that the data you're using is actually clean and solid and all that. If you use raw data without considering the quality of it, without filtering it, your model will be, well, likely something close to useless. So it's super important as a first step for everything to clean up your data. I'm sure most of you know that, for instance, some of the more common sensors that we have on board many ships is like speed logs, for instance, and power meters. They're both very good devices, but they have issues. It's not like you can use the data coming out of those things just without doing anything to it. Speed logs may perform better or worse depending on vessel draft. It's quite often the case that the actual sensor, the Doppler sensor that goes into a speed log, is mounted such that it will work better at higher drafts, maybe not so great at lower drafts. If you know, that's fine. Then you can filter your data and say, well, in this particular situation or in this particular condition of the vessel, maybe it's not the most reliable thing of all. Same goes for the power meters. They're good, but they're also a little bit sensitive. There are components installed on the main shaft that can not necessarily fail completely, but degrade such that maybe the range of output data becomes different over time. Some of them are even a little bit temperature sensitive, but that's a different story as well. All that you need to somehow be able to take into account before you start using your data. And what we do is we're not looking at this manually. We're using what's called convolutional autoencoders, long short-term memory models. That's also a term for more or less the same thing, to sort of consume a baseline of data that we know are good. So that could be maybe a month's worth of data that we've validated through other means, for talking to the vessel and looking at the data, actually physically looking at it and see this is good. Then we feed that into the model, and then every subsequent data point gets filtered through the model. And then the great thing about these autoencoders and LSTMs is that they can then spit out a value that says, well, is this new data point, is this any good or is it bad? And that lets us label all the data so that we can only feed the good data into our models. So that's sort of a basic good step. And the amount of tools out there to do this is enormous. There's such a great amount of help. Of course, you have to know how to use it, but in particular, we use quite a lot of components that the good old-fashioned NVIDIA corporation of great fame these days has made, and we also use some of the tools that are used also in many educational institutions, such as the scikit packages. It's very good. It's out there and anybody can use it, but I think we've gotten to a point where we're quite good at using it. So let's see what we can do with it. See, for one thing, for those of you that are engine people, this view is probably reasonably familiar. It looks like what you get on an alarm system on board. But the special thing about this is that this is cylinder temperatures collected and superimposed, so to speak, over time. So we can follow the evolution of cylinder temperatures through a period of time. You can see sort of the y-axis is a progression of time from sometime in 23 to May of this year. And you can see that there's something going on where the temperatures are getting increasingly bad. At the bottom of the setup, you can see that's mostly green, some yellow. And you get further up, we see fouling is getting worse. And then all of a sudden, we're looking at April, where we have a lot of high temperatures on the cylinders. So that's definitely pointing towards necessary overhaul. Then the overhaul actually happens, and we get to May, and everything is green again. But the main point here is that you can actually follow things along. We actually have some views that are even better at this point that let you see exactly which cylinder is acting up. So maybe if you have a bad injector, you can sort of follow the decrease in performance, and then you get the chance to actually do something to just maybe that injector. That's a cheaper overhaul. It's simpler. Something you can do, the crew can do itself. They do that routinely, of course, but now you actually have some insights from the operations department that let you guide and maybe advise that this is something that needs to happen now rather than later. That actually points to a good set of savings on that alone. Of course, we don't recommend necessarily that you should also always stick with the planned service schedule, of course, but this lets you do servicing or minor servicing steps that would leave your engine in an overall better state and definitely performing much better if you track health and act accordingly. It also lets you get your spare parts in place before you need them. So that's pretty great. On top of that, we're also doing sort of the same thing on hull performance. On this view, you can see the evolution of shaft power over time. This is from, again, sometime in 23 for a particular vessel to sometime in 24. So over quite a period of time. And again, we've used a model we've trained a model on a baseline set of data a couple of months. And the model's sort of expectations for what should happen performance-wise, given whatever conditions the vessel has been subjected to during this period, that's the yellow line you're looking at. And the black line is what actually happened. So you can see during the first period, it looks good. The model predicts very nicely how the hull actually performs, what amount of power you should be putting into you should be using to push the hull along at a particular speed. That's basically what we're monitoring here. But then you can also see that a bit further along, it kind of seems as if maybe we're using more power than we should, according to the model, which would suggest we're dragging something along with us that could be cleaned off and then things would improve. And then at the very end, we get to a point where the hull cleaning actually happens and the black line drops quite a bit below the model. So you actually see it quite significant. I think actually maybe even there was a new coating applied to this particular vessel at this point. So you see a significant drop in fuel consumption, which is good. So this is a very good tool for actually showing off the current state of the hull, what's going on. Are we going to a better place or worse place? And the actual effects of whatever you do once you have the ship out of water and you clean it and you recoat it and whatever you want to do, you can actually measure the performance increase that you get from it. So that's pretty good. Pretty soon also we'll have this split into to a view on hull performance and then on propeller performance in a separate view. This is sort of the whole thing together. Planning these hull cleanings is also, I mean, using some of the robotic hull cleaning methods that are around. It's something that can be done fairly quickly, and if you have the ability to track and maybe superimpose that on your schedule, there's money to be saved there, but by doing that optimally as well. Now, returning to the main engine again, we can also see we have the same sort of yellow line, black line modeling going on here, where we can also track the SFOC compensating again for all the external factors. So this is cleaned out for all the buffeting that happens due to weather and currents and all that sort of thing. So we're looking at the clean power generated by the engine, or rather the SFOC, compared to what the model suggests. And again, in this case, we see sort of an evolution. This is, I think, the same time period, where we see the model predicting quite well what's going on to begin with. And then things look a little bit maybe like they're shifting toward the ceiling of what we would predict. And then at the very end, there's a yard stay and things seem to be dropping off. We don't really have any data to show off here at the very end, unfortunately. So we don't show it off very well, but that's at least what happens here. The yard stay clean, everything should be great. The black line should probably drop below the yellow line. And then we also have at the very end of the graph, you can also see a big black bar, which is what would the model expect if we were to baseline on the period of time that just passed just now. What would the model look like then? And as you can see, the model would actually expect that it seems performance would degrade a little bit. The SFOC would be higher, but then at this point, it doesn't really know about the yard stay. So if you retune or rebuild the model after the yard stay, well, it should be nicely in line with the new performance. So again, cleaning up the data and doing the modeling that we do, you can actually track very nicely what's going on, and you can get into a situation where you can be ahead of things. You can predict, and you can maintain based on those predictions. So all in all, we think we have a pretty good package. Last time we spoke on Digital Ship, we were discussing mainly the basic product that we have, which is the direct fuel savings, which is also a modeling exercise, saving in the vicinity of 10, even 15% at times for CPP vessels, and 3 to 4% for FPP vessels. For the CPP vessels, we're looking at equipment optimization, generating better propeller curves. For the FPP vessels, that's obviously not an option, so it's mostly about improving charter compliance. So basically keeping a set power level, keeping a set speed, or the combination of the two. And then you can get the additional savings from the improved maintenance schedules that come out of doing predictive maintenance. Now, we have a couple of things that we're looking at this point. More stuff will be coming. We will be able to also do some predictive maintenance on auxiliary engines. And then I think importantly also we'll be adding trim and squat, which is more or less dynamic trim advice tooling to our new platform, the one that we showed off at SMM. So it's a full package that has everything from direct savings to advice to predictive maintenance. We like it a lot. And that's pretty much it. That's the story we wanted to tell you today. So thank you very much.
Oh, thank you very much. Are we going into questions now? Yeah.
Yeah.
Oh,
I'll stop sharing.
Okay, so to the audience, we're open to questions in the Q&A box. I've got a few of my own to start off with.
Okay, shoot.
But just like the specifics of what we're talking about, like we discussed before we start, you mentioned turbochargers and pistons before we started. So just the audience get an idea, what specific maintenance tasks are we thinking about here?
So I think for us, it was natural to start with turbochargers and cylinders and exhaust temperatures and that sort of thing. We want to have a good profile of the engine, because if we have sort of a performance profile, that helps us determine how much work we can safely have the engine do, which again feeds into the basic product, the frugal propulsion product. So if we know the engine limits, well, then we can better trim the running margins and then eke more performance out of the engine, or less if things are degrading a bit. So that's basically the core idea that got us to this point. We thought, well, that's pretty interesting. We can do that. So that would in itself be an interesting product to look at. And again, also because we're able to point at individual cylinders and say, well, this guy is perhaps not performing as great as the others. Maybe it needs a new fuel pump. Maybe it needs injectors. At a later date, I can't promise you exactly when we'll be able to better pinpoint exactly which component we think is the culprit in performance degradation. So whether it's the pump or the injector or whatnot. Can't do it yet, but we will be able to.
Wow, well, we've got 3 quick questions if everybody'd like to open the Q&A box. So I think the first one in is for it's Dae-Yuk Kim, who LinkedIn says senior researcher with Abacus in South Korea. Are you considering a resistance due to the weather? I guess we're getting outside the scope of weather performance here, but of predictive maintenance here. But do you want to?
No, but that's a good question. Definitely, okay. Yes, we are considering weather. So for all the modeling that we do need to be able to filter out weather effects to actually clean up the signal, so to speak. So when we do hull performance, we clean out the weather effects to be able to tell what's the raw power that was actually put into the vessel to push it along at a certain speed. That is a necessary step, and that's a very good point. Almost, I mean, particularly for vessels that are sailing in, let's say, for instance, the North Atlantic. If you were to just basically say, well, we can only concern ourselves with good weather days, you'd have nothing left. So you basically have to be able to subtract weather from the data that you're looking at to get a reasonable data set. So yes, we do definitely do that.
Oh, very good. So next question, Yegan MS. Are you taking any reference from the ship trial? I think it means ship trial, not shop trial, or sea trial report for making the analysis or health checks?
Yeah, so definitely if we have it. So for the engine, we always configure our system with the test bed results. So we have sort of the clean, the squeaky clean, super optimal baseline. So we have that configured into the system to sort of measure the distance between that and the current situation. So we do that. When it comes to the hull performance, we will be using at some point. We'll also be using CFD models for that. But at this point, we're basically just baselining out of a particular period that we select to be some baseline period. And we just say, well, this is a good period. This is a known good. It might not be the best, but we call it a known good. And then we track from there, which is also a good way of doing it. If you have complete CFD modeling and all that, you could get closer to knowing which is actually the true optimal for a particular vessel, but we don't need it.
Wow, very good. So next question from Prashant Birada, who's with a Smart Ship Hub in India. What's the baseline criteria for parameters like engine parameters when pre-processing the data? So what engine parameters are you looking
Yeah,
at?
so again, we would go from the test bed results to say, well, these are the safe limits, and we would also look typically at what's been there's typically a report for the commissioning of the alarm system on board, which has all the limit values for cylinders and such to see so what are the practical limits, and those are the ones that we'll be basing ourselves on. So we're keeping in line with whatever is has been part of sort of the vessel project from the beginning.
Oh, very good. So now we're going to Armenia. We're going to hear from Timothy Belarusov. What's the minimum data set frequency for LSTM long, short-term models to run good? Also asking what other critical engine parameters are you monitoring for critical maintenance apart from the temperatures of the cylinders?
Yeah, so for LSTMs, it depends sort of on the amount of noise you have to account for. It doesn't have to be a monstrously huge data set. I mean, if you have a month's worth of data, you're pretty good to go. It's how would you say? Yeah, so it's very much the noisiness of the data set. So again, the weather effects, all that, you have to be able to take that into account. So, but it's not like it takes years or anything like that. You have a month of data, you're pretty good. And then as you get more, the autoencoders will be able to do better. But a month is that's a good place to start.
So the frequency is the months.
Yeah, so and the frequency
period.
for the measurement points, maybe that's also,
Yeah.
in our case, we have we downsample all the measurements we take on the vessels to 1 minute intervals. That's what we do. Could you do with less? Probably. I don't think you necessarily need more. I think that would be overkill to go for higher resolution than that.
Oh, very good. So Simone Calawa is with in Brazil with CEO of Optimum Maris. So she asked how long it takes for the ship owners to recover the investment. So Naveen's already said a few months, and she's got a follow-up question. What about the support for maintaining the installed system?
Yeah, so support for maintaining the installed system is directly via us, or definitely, of course, also the whole Emerson setup has a giant service department. So there's a lot of aftermarket service possibilities here.
Oh, very good. So Chris Huxley Reynard with Applied Satellite Technology Radar, that's in the UK. How do you measure the performance of your models? Do you have data about engine failures? What level of accuracy are you able to achieve?
Yeah, so that's an excellent question as well. We do not yet have a long enough running record on the predictive maintenance stuff to show failure records. But what we can do is we can actually look at the data collection that we have so far and then basically track evolution of temperatures, which point very nicely into the maintenance manuals for the engines. And it tracks and matches up very nicely the periods that we see for degradation seem to suggest that we're definitely measuring the right thing. So I guess that's how we baseline our predictive maintenance. If you were asking about the basic product, the direct fuel savings, that's pretty simple because that can be just simply turned off and on, and then you can do a comparison at a set speed and then see what's the difference. So that's fairly easy for that one.
Well, this next question, I don't know, is it Devanand Sambamurthy? He's a chief engineer in Chennai. He's asking, do you have any data about the MAN GI engine. I think that's maybe out of scope for this webinar. I don't think. Yeah.
No, I don't think we have anything particular on that.
Okay.
Yeah,
GI,
I
what
mean,
is that?
the MEGI engines are basically the high pressure engine. So the system would work actually exactly in a similar way. I don't think we have an installation on the MEGI as of now, but
No,
it
don't
would
think
work
so
in a
either.
very similar way to what
Hmm.
it would do for any other engine.
Yeah.
Well, so Prashant Birada from SmartShip Hub, how are you differentiating the abnormality in engine parameters because of hull fouling or other abnormal engine conditions? I guess that's all sort of within the algorithm, is it? Or is it?
Yeah. So the main point of interest for the hull is to figure out one, how much power are you using to get to a certain speed through water, of course. That's sort of one thing. Then when we're looking at the engine, we're looking at the specific fuel oil consumption. We're looking at how much fuel are we burning to get a particular amount of kilowatts out of the engine. So that's one sort of measurement of both fouling and performance level. And then when you correlate that with the temperatures of the cylinders and the turbocharger, then you can get to a pretty good idea about where are we at performance-wise. Are we in a degraded mode or are we in a good place? Yeah, so that would be it.
For me, for Naveen, on operationalizing this, so if you've got a company with 20, 30 vessels, how would this look like in practice? I mean, is this something going on in the background, or are people checking all this data every day, or is it sending them alerts? Or I don't know if you've done.
Sure. I mean, if you see the platform which is being provided through Smart Propulsion, it gives you an option to look at the fleet, gives you an option to look at the vessel as well. So if I am a superintendent sitting in the office and I have 4 or 5 vessels under me, I don't need to go on the vessel. I can see what is happening, right, sitting in the office or looking at my phone. I just log in. I can see what is happening with the main engine, just checking the critical parameters. Uh, there are some parameters like exhaust temperature, pressure, which they probably have a look at it. And if it's normal, that means everything which is associated with that is normal. So super, it makes the life of the super much easier because he just can check it on his palm on what is happening on board. And of course, when he needs to, and if some of the superintendents, I mean, some of them can be a data enthusiast, and they can see a lot of data, and they can also kind of troubleshoot with the data as well of what is the trend which is there. So there is also a history which is stored, which can be downloaded based on the tons of availability of data which is there. It can be on the process parameters, it can be the SFOC, it can also be some of the interrelated parameters. It can also be on the CIIF front, which also can be readily seen on the dashboard. So for a week, whether the vessel is meeting the A, B, C, D, E CIA rating, that also very much, very well can be seen by the superintendent. So they can really take an action based on this particular data.
So they might say, I'm worried about these cylinder temperatures I'm seeing. Can I run the algorithm and see if there's a different pattern to what it normally looks like? Or
The algorithm are running always on the background, so you will always see like what could be an expected trend for that particular parameter and what is the actual. So if there is a deviation, the superintendent or the technical director will get to know.
oh. I mean, it's very different looking at data and looking at algorithms is what I mean, because one thing's just seeing the picture right now, another one is seeing where's
Yes.
the trend going, or is it more like I'll explore what's happening, or is it more like an alerting thing with a
Well,
It's absolutely alerting. I mean,
sorry.
they can of course explore the data which is there, but it's alerting in a real time basis. So as I was mentioning, like when the Frugal team developed this technology, they tried to keep it as simple as possible, so that if there is a fifth engineer, if there is somebody who's just been on the board in the first month, he will be able to tell there is some deviation there. Because if this system is not there, for instance, when you're just looking at the exhaust temperature, most of the occasion you have an high and low temperature setting over there, but sometimes these settings may work, may not work, and with this technology you are able to see based on the history, based on the real time data, not just for that parameter but also taking into consideration the AMS, AIS, everything all together. So that is why this is different as compared to some of the what engine manufacturers are providing.
Oh, yeah, because the engine's getting enormously complicated, and a lot of people have a little bit of knowledge, but you can't possibly understand everything with a complicated engine these days, and that's what the system can do. Yeah. And for last, so what's the actual machine learning component of this? I guess it's continuously building a better model of what good looks like. Is that what is that
Yeah,
what the computer's
exactly.
doing?
So for basically almost everything that we have running modeling wise, it's very much a question of baselining, figuring out what does good mean, and then tracking changes based on that sort of good state. Saying, well, are we moving away from it in a bad direction, or is it maybe getting a little better? Because then we can re-baseline, find the new good state, and then move like that. And then, of course, we have hard configured limits that basically say, well, this is for instance the highest temperature that we could possibly accept for the engine and things like that. Yeah, so it is figuring out what's the good state that we want to be at, and then tracking things from there. And as I think I mentioned it at least, then the good state can be sort of initially it could just be some period of time, and then we'll just go from there and learn as we go along. If that was actually wrong, we'll figure out what was the correct period of time to consider the good period of time. And then we can actually also do labeling of the data. So if we know, for instance, or actually the vessel owner himself can label the data. So once it's been at a yard and done the whole thing, he can label this as a known good state. And then we move from there.
So is it a one-off process training it over a month, or is it continually?
No, it retrains every now and then. So just to be sure that we are not basing ourselves on something that's not actually true.
Oh, so over time you get a very, very good model, even better and better, that's good at spotting things.
Yeah, and you can even end up having a collection of models that show how are things doing when it's bad and how are things doing when it's good, and then you might be able to do interesting stuff with that as well, which we haven't done yet, but that will also be coming. So there's a lot of fun stuff you can do if you have that sort of. You could say it's sort of like a snapshot of how things should perform at a certain level of degradation, or however you want to put it. And it gives you some good opportunities for figuring out how things should perform.
Oh, very good. And perhaps as a last question, so the sort of currency, how people judge these things in the big picture is the percentage fuel saving. We keep hearing about, wind can do, if you put sails on your ship, you get 16% savings, or maybe, well, these are the kind of numbers we hear. But you had numbers about better modeling of how to adjust the controllable pitch propeller of 10 to 15%. But I mean, assuming companies are doing that already, I mean, just from having better maintenance of the engine. So it's 3 to 4%. I think you said cost saving, not fuel saving. But I mean, is that a number that companies can go out and say, look, this is something can really use to?
Yeah. So at least
consider?
from the performance perspective, definitely. I mean, if you keep track of if there's a single cylinder, for instance, that's not doing well, and you are able to fix that injector or fix that fuel pump, then the performance bump you get from actually doing that could easily be 3 to 4%. So yes, that can happen, something like that. But again, that assumes, of course, that you're going from bad state on a cylinder to a good state. So that could happen, that's for sure.
You're not leaving yet. We've got 2 more questions come in here. So,
Oh, good.
So it's John Kokoragis from Bureau Veritas again. He's saying, is your model described anywhere? So I just looked up CMAC. It's a forum for technical interchange with parties interested in piston engines and.
Oh, we haven't. So the components that we use to do the actual modeling are well described, but we haven't published anything on it yet. We might, but I think I would have to talk to the board about how much publishing we can do on it. But that could happen, maybe. But again, the software components we're using are very much public.
Okay, well, it's stuff you develop yourself, though. Oh, it's sort of public.
Yeah, so I guess you could say the modeling algorithm that we made is pieced together from well, quite a lot actually of available components that are out there that are being used for data science in general. Again, a lot of the stuff that NVIDIA has been doing is extremely useful in all of this, and we are using that extensively.
Okay, wow, that's the machine learning side of it, not the engine side of it. I guess that's what.
Yeah, exactly, the machine learning side of it.
Oh, okay, so this last question, I'm not sure it's in our scope, but it's so Pragyan Gupta from Avkalan.ai engineer. He's asking what features in a machine learning can we use for a ship routing system? And how do we make it dynamic for current
Ah,
running
yes.
situations? We
That's
didn't talk
a-
about ship routing, or you want to?
No, well, but it's a super good question. It's actually also
Good.
something that we are looking into, but I think that might also be the subject for another talk. I think it's a giant subject in itself. Yeah.
Yeah, we can. I think that's off the
Mm.
scope. So Parash and Birar from Smart Ship Hub. Over a period of time, the baseline of vessel parts changes. So you need dynamic thresholds to identify anomalies. Is that something you're considering? So yeah, I guess the
Yeah,
parts
so
wear out.
I guess you could say dynamic thresholds. That's true. For instance, for the hull performance, we do dynamic thresholds because the draft very much points into. I mean, you couldn't consider every value for hull performance to be the same because draft changes a lot. So that's one of the dynamic variables that goes into figuring out how to sort of baseline hull performance. That's figuring out, well, how do we sort of level out the draft so the values become comparable after all. So that's one of those parameters. For the engine, same, you could have some dynamic. It's not so necessary to have dynamic parameters for the engine. They're pretty fixed, sort of the good, bad definitions by the engine manufacturer in the end.
Oh, very good. Well, that's a lot of questions. I think it must be pretty exhausting.
Yeah, that's
now.
good.
I guess we're gonna
Questions are good.
Start bringing things to a close. I don't know if Naveen, you'd like to any closing words you'd like to leave the audience with? You're on mute at the moment, by the way. Or how do people move forward with this? Should they contact you? Or?
Yeah, sure, Carl. I think the audience can contact me or Lars on this front, and then we will basically we can answer the question and also see how the system can be implemented on board the vessel. Again, I think this is how we are positioning this is a complete package. Because when we talk about the smart propulsion, it's something where you get the 15% saving for a CPP, 5% for an FPP. But what if you add something on the predictive, which again is an operational cost? So I think it's a complete package which we are looking at. There are quite a great references which exist now. And I think we are really confident that this could really help the super and the technical directors for a shipping company or a ship operator.
Oh, Lars, would you like to leave any closing words?
Yeah, it's an absolute pleasure to talk as always. It's great, and we're expecting quite a lot from this predictive maintenance. The interest at SMM was pretty great, surprisingly great even. Watch this space for more, I guess.
No, very good. I can't remember ever doing a webinar on predictive maintenance on engines before. It seems to be a whole new subject for just to open the door on. So thanks everyone for watching, and I shall pass back to Farah for the closing words. Cheers.
Thank you.
Thank you.
We'd like to thank our guests Naveen Bhushan Hegde and Lars Stoustrup for joining us today. This webinar will be on our YouTube channel. We'll be sending you a link and contact details if you have any more questions. We're back on the 1st of October with Ocean Op and Better Sea. You can check it out on our website to register. Bye.
Bye-bye. Cheers. Bye.